Good morning. In behalf of the Let's Talk Science Committee and the Low Vision and Hearing Challenge Committee, I want to welcome you to this Let's Talk Science lecture series. There are few in this audience who are not familiar with some form of visual impairment, so a presentation on vision restoration should be of interest to us all. And we're fortunate to have as our speaker a distinguished leader and researcher in ophthalmology to bring us up to date on recent advances in vision restoration. Afterwards, we'll have opportunity for question and answer. I've asked Jenny Stimson, Chair of Low Vision and Hearing Challenge, to introduce our speakers.
Russell Van Gelder has been the speaker that we've gotten the most positive feedback of any speaker our committee's invited. And so we're so excited that you're back. Each time you speak, you leave us with something exciting that's about to happen. And so we're eager to find out. Last time you were here, you said you'd gone to a medical research convention where you learned about restoring cells in the body, and you imagined how that could apply to the retina. So to have you come today and talk about progress in restoring vision is what I've been waiting for. Thank you for being here. Dr. Van Gelder, as you see here, has distinguished positions associated with the University of Washington Department of Ophthalmology. I loved reading that his goal is to give each patient the care he would give his own family, to apply the best scientific evidence and most appropriate treatments, and to help patients make their own best medical decisions. Wow, isn't that what we're looking for these days in medicine? Yes, I think it's very exciting. So he's an active clinician, scientist, and a teacher. And, you know, he's involved in all the things that a researcher is, like research journals and going to conferences, presenting at conferences, but then learning from conferences as well. And I had to look up again how to say this, but his specialty is about the lining of the eye, the uvea. So uveitis, that's his specialty. But you'll see from his talk that his knowledge goes beyond. We welcome also Catherine Beard, who works with him, and she's here to be a support to him and to us in this presentation. So thank you for being with us also. Thank you.
Thank you, Jenny. Well, Jack and Jenny, thank you so much for the very kind introduction. This is my third time speaking here. At some point, I'm going to give a very bad talk and you'll stop inviting me to come back, but hopefully it won't be today. And I'd really like to thank everyone for coming out. Now, as I understand, this is, I think, my first time doing the science, specifically science. I've done sort of the medicine talk. So just so I have a sense of the audience here, first, the easy questions. How many of you have seen an ophthalmologist in the last year? Yes, okay, very good. That's called employment security. And how many of you have ever had eye surgery done? Yeah, that's almost everybody. Okay. How many of you have training in a science? Okay, that's about half the crowd. And how many of you have a graduate degree, a master's or a PhD or an MD? Okay, about half the crowd. Good. So that helps me know where to sort of pitch the talk today. So we're going to talk about the eye as a camera and what happens when the camera breaks and how we fix the camera. And what I'm going to spend most of the talk going over are three vignettes of research being done in our department, which I think much of it is, or some of it is not published. This will be new to at least some of you. And I hope it instills some optimism that we're going to crack some of these problems that have been difficult and have caused a lot of people to lose a lot of vision over time. When I'm with my patients, I often tell them that the eye is like a camera. You have your lens, which we have a cornea and a lens. You have your film. In this audience, I can say film because you remember what that is. My kids are like, film? What's that? So the retina on the back of the eye is like the film. It receives the image and it converts that image into electrical signals, which go to the brain and are interpreted. About somewhere between a quarter and a third of your brain is devoted just to decoding the signals that are coming out of your two optic nerves. So a very large part of what you do mentally is around making sense of the visual world. I want to start with a story of progress, because I think in this day and age, there has been a de-emphasis on understanding how much scientific progress we've really made in our own lifetimes, or certainly in those of ourselves and our grandparents. And I'm going to start with this picture, which I think I've shown here once before. I was at one of the meetings that Ginny alluded to in Paris a few years ago, and had a free afternoon and went to the Musée d'Orsay, the fabulous art museum. And there was an exhibit of the original daguerreotypes. So Daguerre invented photography in the 1830s, and there were a number of photographs from Daguerre himself and photographers of that era. And this picture was taken in about 1850. And it's a beautiful photograph of two sisters. If you're a photography buff, you can look at the tonality of this and the composition. I mean, for 1850, this is really an amazing photo. But what caught my attention was the sister on your left, because if you look carefully, she has a white pupil, and then the other is normal. That's a cataract. That's probably the first photograph of a cataract from 1850. You don't see people in France or the US anymore like that. When was the last time you saw a young woman walking down the street with a white pupil? We don't see that anymore. So you're all familiar with cataracts. I suspect almost everyone in this room who raised their hand that they've had eye surgery has had cataract surgery. Cataracts really do degrade vision. This is one of my favorite stories is Claude Monet, who developed severe cataracts in his 70s and 80s. And if you look at the same water lily pond paintings that were done in, say, 1899 and where he is in 1922, you'll notice not only has he become more abstract, but his palette has changed completely. And it's all now yellows and reds. And that's because that's all he was seeing was yellows and reds. That's the light that his lens would let through. His blues and greens were gone because of the cataracts. So why did that young woman in 1850 not have cataract surgery? Well, we have to think about what cataract surgery was in 1850. The process of doing cataract surgery is ancient. It goes back to about at least 1,000 of the current era. And it was a technique called couching. And in couching, you take a long needle and you hold it in a flame. And then you hold the patient down and you stab into the eye and try to get the lens and push it out of the way. This is a picture from 1500. This is called a couching chair. And you can see that it has some nice red ribbons on it, and those are designed to hold the patient down so that he can't fight you when he's about to get his eye couched. And honestly, at 1850, when that young woman's picture was taken, this is a picture of cataract surgery in 1850, a print. And it's not terribly different. You have one person holding the patient back. You have the surgeon, no gloves, you'll note, ready to do the procedure. And as a reminder, the ether dome was in the late 1840s. There was really no anesthesia at this point. You got a shot of whiskey and that was about it. So you could imagine why the young woman said, my other eye is pretty good. I'm going to leave well enough alone. I don't really want to go through that. Monet did have cataract surgery, and by 1920, it was a more advanced surgery. There was anesthesia, for example, and the techniques had advanced. But here's Monet recovering for 2 weeks after his cataract surgery, in which his eye was basically sliced in half and the lens was removed. He had a complicated course after surgery. Some of you may remember your grandparents having cataract surgery in the 50s or 60s and spending a week or 2 weeks in the hospital with sandbags on either side of their head so they couldn't move. This is a very interesting set of paintings. This is the same scene that Monet painted with his eye that still had a cataract. He only had one eye operated on. And here's the same scene after his cataract's removed in the other eye. And you can see that the palette has changed completely. And in fact, for the aficionados, the lens of the eye has much of the ultraviolet absorbing properties. And so in 1923, there were no intraocular lenses. You didn't get a plastic lens at the time of surgery. You were left aphakic, meaning without a lens, and had big Coke bottle glasses. you can actually see infrared when you take ultraviolet when you take the lens out. So some of those purple colors there probably were on the ultraviolet end of the spectrum, which he was able to appreciate with his short wavelength cones. So let's fast forward 100 years, and now we're talking in 2025, and this is...
Acclimated, pay attention to the screen while acquiring the section required to stabilize the eye.
This is sped up a little bit, and we'll just turn the sound down on that. Let me see if I can... There we go. So this is femtosecond cataract surgery. I will say we don't really do this at UW at this point. Oops. But what's happening here is the surgery is actually being done in large part by a computer-driven laser. And so the surgeon basically says where he or she wants the incisions to be made. There will be an incision here, an incision here. The lens will be opened up. The capsule will be opened by the laser. You set all this up on a screen. The patient is just lying there, but the surgeon is really at a computer right now, not at the head of the bed. And then OCT, which we'll talk about in a minute, optical coherence tomography, reads the cornea and the lens directly, looks at the lens, figures out where the incisions need to be made. And then the surgeon draws the incision that they want to be made. And you just saw a circle form there with bubbles. That was a laser opening up the anterior capsule. And now you're going to see wounds being made here and here, right there. The lasers just made the entry wound, and right there, a paracentesis wound. So now at this point, the surgery goes back to being a manual surgery to take the lens out, but about half the surgery now was really done with no-touch technique. And this is all done under local anesthesia. I'm not going to go through the whole surgery here, but suffice to say, it's about 7 minutes to remove that cataract. And you go home that day and you see that day. A lot of places don't use a patch anymore. This is very different than 1850. 3.3 million of these surgeries, cataract surgeries, were done in the US last year. Think about that. That's one every 8 seconds. It's so routine, a lot of people treat it like a dental cleaning. Oh yeah, I have to get my cataract out this morning, but we can have lunch at 12. I'll be done by 10, you know. When we think about medical progress, this is what we're talking about. A situation that was a blinding, almost universal disease 100 years ago is now, for most people, 99% of people, a mild nuisance to get it done. And many people's vision is better after cataract surgery than it was at any time in the 30 years before they had their surgery done. So when we think about the challenges we have today, cataract in the US is not a huge challenge. It's a socioeconomic challenge. It's a cost challenge, but it's not a technical challenge, not a medical challenge. But macular degeneration, glaucoma, and diabetic retinopathy all remain real challenges and cause a great deal of blindness in the US. When we look at the incidence of these diseases, they are very, very prevalent. Now, cataract is extremely prevalent. When we think about cataract, by age 70, about 60% of people have a cataract. By age 80, it's getting up towards 80%. So if you made it to age 80 without having your cataracts done, you're in a very small minority. This is pretty much a universal fact of aging. But macular degeneration is also very, very prevalent and very age dependent. And this is for the wet form of macular degeneration. By age 85, it's affecting about 15% of the population. And I won't compromise your confidentiality, but I am sure that there are a number of you who are getting injections every month or every 3 months for your macular degeneration in this room. And in fact, if you look to your left and you look to your right, I can pretty well guarantee you that at least one of you has signs of significant macular degeneration in this audience. And our treatments are better, but I think none of you would say, oh, it's like cataracts. You go once, it's done. I mean, this is a major impact in your life, even though we can do much better now than we could 20 years ago. When you combine that, of course, with the demographics of the United States, and you look at how many people are anticipated to be at certain ages, the number of individuals in the US by 2050 who will be 65 and over will be 90 million in the US. The number 85 and over will be 30 million. That's how many 65-year-olds there were in 1980. So from our perspective as ophthalmologists, we're on a burning platform. We have a huge population growth in number of individuals who are getting to the age where they get these age-related eye diseases, and we don't have solutions for diseases like macular degeneration or glaucoma at this point. We have treatments, they're partially effective, they are not cures. So that is our charge, is to try to figure out how can we turn macular degeneration, glaucoma, diabetic retinopathy, retinal detachment, corneal decompensation, all of the things that cause blindness into something that's fixed as easily as a cataract is today. So a little bit about who we are, and I think I went over this last time in the talk as well, but we're your neighbors down the street. Catherine and I walked down here. It took us 8 minutes this morning. So we're just down the street, down 9th Avenue at James Street. The Eye Institute is based there. We have the whole 7th floor of this building and a little bit of the 8th floor. It's about 25,000 square feet of space. Our mission is to alleviate suffering from eye disease in our community and worldwide. It's a pretty simple mission. We don't want people to suffer from blindness. We do that by providing care, by furthering the state of the art of that care with our research, and by teaching others to do what we do. Those three missions are interrelated, and when you come see us, you will see all three parts of the mission. You will see our trainees. Every patient who sees me sees my resident, my fellow. Why? How are they going to learn if they can't see the patients and learn from the patients? Our research is intimately tied to our clinical care in ways we'll talk about in a few minutes. So all of this makes a sort of holistic whole in advancing our mission. And it is unique to us. If you go to any other eye clinic in Seattle or any other non-academic eye center, you're not going to get all the parts of that mission. In terms of clinical care, we saw about 60,000 patient visits last year. We are the safety net for King County. We are based at Harborview. We see everybody. I mean, literally everybody, from the wealthiest people in the world to the poorest people in the county. We have the only trauma service in the Northwest. So if you get into an accident where your eye is injured, you're coming to us. We provide all the subspecialties, including the rare stuff like uveitis and ocular oncology and hereditary retinal disease, and patients like us. And we do very well in terms of our patient scores. This was a nice picture last year of our graduating residents. We turn out 5 ophthalmologists a year. This is way under training. So in Washington State alone, there's about 18 ophthalmologists a year retiring. And our program is large enough to turn 5 out a year. We'd love to do more, but there are constraints in terms of the funding for these individuals that have kept us at 5, although we will expand to 6 next year. We're also the academic program for all of the surrounding states. There are no residencies in Alaska or Montana or Idaho or Wyoming. And so as part of the WWAMI system, we really provide the training grounds in the whole Northwest for ophthalmologists. To become an ophthalmologist, it's about 10,000 hours of training. So it's a 4-year residency, one in medicine, 3 in ophthalmology. They do about 9,000 hours of hands-on training, kind of the Malcolm Gladwell 10,000 hour thing. We also train about 30 medical students a year and introduce them to ophthalmology. And our residency is super competitive. We had 600 applicants last year for our 5 positions. And we get very, very, very good medical graduates to come here for training. About half of them stay in the area. So odds are about 50-50 that any ophthalmologist that you see in the community did some training time with us. Okay, but this talk is about research. So let's talk a little bit about research, and I'm going to share a little bit of background as to the broad palette that we have, and then I'm going to focus in on 3 particular interesting scenarios. So overall, we have 29 researchers right now at UW who are doing primarily vision-based research. We have about 48 federal grants, which total about $25 million a year in funded research. That puts us up in the top 3 nationally for the size of our program. We'll talk at the very end about how this used to be a bragging right and now it's a huge vulnerability. But we have a very vibrant, the point is we have a very vibrant community here. Most of our vision research is actually based just up the road in South Lake Union. This is the SLU, E, and F buildings, which are between Mercer and Republican and Dexter and 9th Avenue in South Lake Union. The whole second floor of this building and most of the first floor are vision research. And as we'll talk about in a second, the Corrales-Johnson Retina Center and our clinical research activities are in the F building. The Corrales-Johnson Center opened in 2019. It's a dedicated facility for retina. And so we only see patients with retinal or inflammatory diseases there. We've seen over 50,000 patient visits there since it opened in 2019. This is a picture of me with Angie Corrales-Johnson. Some of you who are Seattle natives may have seen Roger Johnson as your ophthalmologist when you were young. Roger saw an enormous number of patients in a very, very long career. He passed away in 2008, and Angie has helped keep his legacy alive by giving a very generous donation to allow us to set up this unique resource. It is our only resource that is mixed research and clinical, meaning that we have clinical trials going on side by side with our routine clinical care, and that's a great model for advancing the field. Okay, let's talk about some vignettes. So vignette number one is imaging the retina. You can't treat what you can't see. So if we're going to make progress in restoring vision, we really need to know at a very fine level what's happening in your eye that it makes it difficult for you to see. Now, when I trained as a resident, which is about 30 years ago, our main tool was to use the ophthalmoscopes. You may remember the one that your internist doesn't know how to use. And kind of tries to look into your eye. We have better tools than that, but even with the better tools, this was the image that we would get. Optic nerve is here. This is the center of a healthy retina. This is an example where you can just look in this eye and say, oh, this patient has macular degeneration. Those yellow spots there are called drusen, and that's a very specific sign of macular degeneration. But you can imagine that's a limited tool. It doesn't tell you what's really going on at the base of the disease. About 30 years ago, Jim Fujimoto, who was a professor at MIT, came up with a technique that has really revolutionized our ability to see the retina, and it's called optical coherence tomography. It should be optical, not ocular. So what is this technique? And I know about half of you have a science background, so forgive me if I'm oversimplifying, and the other half who don't, forgive me if I'm making this too complicated. But basically, we're taking an infrared laser with a wavelength of about a millimeter and bouncing it off the retina, and then measuring the interference of that laser with its own beam. And it turns out if you take a spectral transform of that reflectance, it tells you what the protein content is of the tissue that you're going through. And you can map that physically. Functionally, what that does for us is it lets us have someone sit in front of a little machine like this, acquire this image, which takes just a couple minutes, and it's effectively a microscope slide of the retina. Prior to the development of the OCT, the only way you would ever see a picture like this of someone's retina was after they passed away and you had their eye and you did histology on it and cut it up and put it under a microscope. The resolution on these is approaching single cell, and we'll show some examples where we've gotten to single cells. That is, we can see every single cell in the retina and figure out exactly where the problem is. Is it that the photoreceptors are dying? Is it that the optic nerve is dying? Is it that there's blood vessels growing from the deep layers of the retina where they're not supposed to be? So this was a huge advance, but it was static, meaning that you just got a snapshot still picture of the retina. So Ricky Wang, one of our faculty members, started souping up the OCT, and he's a bio-optical engineer. And what he did was he basically sped up that acquisition process from about 1,500 hertz, 1,500 acquisitions per second to 150,000 acquisitions per second. So this is a hot rod OCT that he built. And when he started looking at the images from this, he noticed something very interesting, which is that they weren't all the same. So if you're getting 150,000 scans a second, you can follow those scans in time. And what he noticed was that the signal he was getting for about half the second was different than the other half of the second. And he kind of put two and two together and said, That's got to be when the heart is beating. That is, it's systole versus diastole, heart contracted, not because the extra blood in the retina was changing the signal. So he had the brilliant idea of saying, why don't I subtract the image that's happening when the heart is contracted in systole, subtract out the diastole when it's relaxed, and see what the image looks like. And here's what the image looks like. This is a perfect picture of the blood flow in the entire retina. Every capillary shows up here because when the blood is flowing through, you get a different signal than when it's not. I can't tell you what a revolution this was for us to be able to see the vasculature of the retina in this level of detail, non-invasively, no dyes, no angiography, just sit in front of the camera and we can visualize your smallest capillaries. And these capillaries are on the order of 20 to 50 microns in size. I mean, these are just tiny, and this is in a live person just sitting in front of a camera. To look at how accurate this was, Ricky did some animal experiments, and he did a technique which is called latex casting. So when you sacrifice an animal, and then you basically perfuse its whole vasculature with latex, molten latex, and then you can dissolve away the tissue and see exactly what the blood vessels look like. Before he did this, he went ahead and did OCT on the same animal. This was in a mouse. And the top pictures here, A, B, and C, are the latex casts, and the bottom pictures are the images that he got from the OCT angiogram. And you can see they are just about identical. We're seeing everything. So this is a huge advance for us. But our researchers were not done. So Ram Sabisan, also in our department, also a biooptical engineer, realized that there was a whole nother level you could apply to this. And Ram had done his PhD at University of Rochester, where he worked with a guy named Dave Williams, who introduced the idea of adaptive optics into ocular imaging. So what's adaptive optics? Many years ago, many of you will remember the Hubble Space Telescope going up. And there was a problem with the Hubble in that one of the mirrors that was in it was a little bit warped. And it doesn't take much warpage to ruin a billion-dollar satellite. What the engineers realized is that they could make a deformable mirror to correct it and program that deformable mirror to exactly accommodate for whatever optical aberrations were in the pathway. This is also used now widely in astronomy for ground-based telescopes when you have to compensate for example, heat waves in the atmosphere. And it's called adaptive optics. Well, David Williams at Rochester realized what a great thing to apply to the eye. So what he did was create a camera that had one of these deformable mirrors in it, and he programmed the mirror to essentially compensate for all of the optical aberrations in the eyeball, the cornea, and the lens. And when you do that, you can actually see single rods and cones, and we'll see that in a second. So you can see the single photoreceptors in the eye. Ram's brilliant idea was to say, well, gee, why don't we take that and marry it to the OCT? What could we do if we could get that level of temporal resolution, that is 150 kilohertz of acquisition, at a spatial resolution that's on the order of about 10 microns? And what he came up with is called optoretinography. And again, to try to pitch this at a level where everyone will get something out of it, the mathematicians forgive me on this because I'm going to simplify this to the level I understand it. But one of the things that you have to do with this OCT is you have to do a spectral transform to understand the data, meaning that when you get that signal where it's interfered with itself, you run it through a Fourier transform and you get a spectrum out of it. Those of you who remember your calculus will remember when you do integrals, there's always an extra term, that plus C term at the end, right? That you always throw away because it doesn't mean anything. And OCT also yields a plus C term, meaning that there's a phase associated with the spectrum, but that phase is on the order of 10%, 1 to 10% of the wavelength of the light that you use, and that would be on the order of 10 nanometers, okay? 10 nanometers is about the width of 3 molecules. It's a very, very, very small distance. Well, it turns out if you're at 150,000 kilohertz, when you stimulate, you can see changes in that phase term that are occurring on the order of a few microseconds, because that's how fast you're sampling. And with the adaptive optics, you have the resolution to actually see that at a single cell level. So in this picture, those little white dots there, those are individual cones in someone's retina. So you're looking at the individual photoreceptors. And what Dr. Sabison has done here is he's put 3 bars of stimulation. So he's got 3 red bars that he is going to flash on the retina over that area. And then he's doing this super rapid adaptive optics OCT. So this is 1/3 of a second before he flashes the light. And this is the outer plexiform length. So he's basically measuring the length of the photoreceptor in the OCT. And then he flashes the 3 bars, and 1 second later, you can see that these have shortened. This is in nanometers. So they've shortened by on the order of 100 nanometers, 1/10 of a micrometer. Why is this important? Well, this now gives us the ability to look at the function of the retina at a cell-by-cell level to the response to any kind of stimulus we put in the eye without the patient having to say anything. We don't have to say, do you see the E? Do you see the Z? We flash, we measure, we have function. So you could imagine if we had a drug that we thought would help your dry macular degeneration, and we really want to see if it works, we test you before the drug, we test you after the drug, and we say, yes or no, this helped your photoreceptors see better. This is the future of where we're going for endpoints in these studies, and our hope is that this will be much more sensitive than waiting for you to drop 3 lines on the eye chart to say something is working or not working. So we're really excited about this technology. Okay, vignette number 2. So this is stem cell regeneration of the retina, and Ginny alluded to this, and I want to give you some update. This is mostly coming from the lab of Jen Chow, who's one of our senior retina clinician scientists, and Tom Ray, who's a basic scientist in the department of what was biological structure and is now neuroscience. So when we think about acquired retinal degeneration, actually, let me back up one more here. What's actually happening in macular degeneration and also diseases like retinitis pigmentosa is that a whole layer of the retina is dying, and that's typically the photoreceptive layer. In the retina, light would be coming in from the bottom, and it actually has to go through the whole retina before it's absorbed by the rods and cones, which are in the outer retina. And where the light is actually absorbed is all the way at the outermost edge here in what we call the outer segments. When you have a retinal degeneration, this whole layer just disappears, and you're left with the 2 inner layers. That'll be important later in the talk, what we do with those inner layers. But at this point, the problem is that your photoreceptors are gone. So one of the ways we would love to treat disease is to regrow this layer, right? That would be perfect. There are animals who can do this, salamanders. So if you take a salamander and you rip its retina out, it will regrow the whole retina. Zebrafish can regrow a large chunk of the retina. Somewhere we have forgotten how to do this in evolution. And the question is, can we, in some way, regrow that retina to restore function? So one of the routes to doing this is using a technique called inducible pluripotent stem cells. Now, what is a stem cell? A stem cell is a cell that can become anything. It's like a kid going to kindergarten. It could become a doctor, it could become a lawyer, it could become a felon, whatever. It all depends on the environment that it's in and what its developmental course is. For many years, it's been known that the embryonic stem cells, which are really the cells before about the 3rd or 4th division of the embryo, each of those cells can become anything in the body. It can become hair or bone or retina or brain. And then after a few days, cells become differentiated and they can no longer become everything. And cells have more and more constricted fates as time goes on. There was a huge ethical, moral overlay to stem cell work because these stem cells came from embryos. And many of you remember in the 90s and early 2000s, there were moratoria on this type of research, and it was quite controversial, and appropriately so. But about 15 years ago, there was a discovery that kind of put a lot of that off to the side, which was this discovery that you could create the exact equivalent of embryonic stem cells by de-differentiating existing cells. So the idea here is to take, say, a cheek cell or a blood cell and treat it with certain proteins. And those proteins would basically take this high school graduate and put them back in kindergarten so that they could become anything. And we call those iPSCs, or inducible pluripotent stem cells. So Jen Chow's lab and Tom Ray's lab have been working on this for a while, actually. And this is an example of a particular type of cell in the retina called the retinal pigment epithelium, which is at the base of dry macular degeneration. This is the cell type that we think is fundamentally dysfunctional in dry macular degeneration. And you're looking at 3 different stains of cells here, where the green is the stain, and it's just a protein called ZO1 that's found in the RPE. Normal RPE, and this is from a fetal sample, an autopsy sample. The normal RPE looks like a perfect little honeycomb. The cells are hexagonal. They're beautifully arrayed. This is RPE that's generated from an embryonic stem cell line. And this is RPE that's generated from an inducible progenitor stem cell line. And the point of this slide is you can't really tell these apart. They look identical. And in fact, in every test that Jen has done on these cells, they are identical. They express the same proteins, they have the same fate, and so forth. So the idea then becomes, well, gee, maybe we could transplant these cells in, and they would use the existing cues around the retina to become re-educated and become the rods and cones in the other cells that have died. So to that end, Jen and Tom Ray did the experiment. They took about 1 million of these stem cells. They labeled them genetically with a green fluorescent protein so they could follow them. And they injected them underneath the retina of a macaque monkey. And then followed them over time. So this is the picture of the retina immediately after the cells were injected. And you can see the green here, that faint green. Those are the cells basically in solution right after the injection. And they followed the animal for 3 months. So at 1 month, this is the picture of the retina without the filter to see the green fluorescence. Here's the filter with the green fluorescence, and here's both of them put together. You can see at a month, those cells are still alive. They're still glowing. If the cells die, they stop glowing. At 2 months, the cells are still alive. And something interesting is happening, which you can see clearly by 3 months. These cells are making processes that are going into the optic nerve. Okay, those are basically ganglion cells. That's optic nerve cells that have been generated by these undifferentiated stem cells. They have turned into appropriate retinal ganglion cells, and they are heading in a beeline to the optic nerve where they belong. This is very encouraging. The cells didn't die, they didn't proliferate into a cancer, and they started to turn into the types of cells that we would expect to restore vision. Now, as encouraging as that result was, Tom Ray's lab took this in a slightly different direction. And they said, okay, we can make cells then turn into other things in the retina. They seem to survive. They seem to become functional. And he went back and asked, how does a salamander do it? And started studying the salamanders. And what he discovered was that there were a couple of proteins that got turned on in a cell that no one really understood the function of, called the Mueller cell in the retina of these animals. And it was those Mueller cells that turned into the rods and cones and nerve cells. And so Tom's lab identified the specific proteins that it took to turn a Mueller cell into a retinal cell, a sensing retinal cell. And then he packaged those proteins into a couple of viruses and introduced those viruses into the eye here of mice. And what he actually, this wasn't even mice. This was in human organoid culture. So we have the ability now with these stem cells to basically create little eye cups in a dish out of the stem cells that have many of the cell types. If he took the organoid culture and introduced these viruses, he got differentiation of cells that look like this. And this is a cone. That is clearly a cone cell by its shape and also by its function. So where are we going with this? We're still enthused about the opportunity to do stem cell transplants, but we're more enthused right now about the ability to try to transdifferentiate your own cells that are still in the retina to regrow that retina. Because then we get around all of the issues that we might have with poor differentiation, tumor formation, if we're using someone else's cells, rejection. This is your own cells basically doing what a salamander would do to regrow the missing cells in the retina. So very exciting. There's a second use of these stem cell technologies which Jen's lab is using, which I think is also really exciting. I mentioned these organoids. So what one does here is take a cheek sample or a blood sample, and then through a very laborious cell culture method, which takes about 4 months, we can grow these little eye cups. We can grow hundreds of these little eye cups from your blood. And each of them is a little model of your eye. Now, it's not a functioning eye. You can't transplant it back in, but it has rods and cones and retinal pigment epithelium and all the things we would expect. What Jen showed a couple of years ago was she took a family that had a hereditary retinal degeneration called Sorsby's fundus dystrophy. You'll never meet anyone with this. It's a very rare disease. But what she realized is if we can grow a normal retina in a dish, we can grow a retina from someone with Sorsby's. And so she grew these out as organoid. And again, you can see some of the cell types that grew here. And then she started to do biochemical assays on the organoids. And what she discovered was that the Sorsby's patients had a deficiency in a metalloproteinase called TIMP3 that was very clear when she assayed those little eye cups for their enzyme activity. Well, how does this help us? What it opens up is high throughput screening. So let's say you have a familial eye disease, genetically determined eye disease. We take your blood, we turn it into little eye cups, and we ask, what of the 15,000 FDA-approved drugs that are out there today, if we drip on that eye cup, blocks the disease or slows it? And particularly for things like dry macular degeneration. For those of you with dry AMD, we would take your blood, make your eye cups. It turns out that if you have severe dry AMD, your eye cups will have some signs of it, especially if we stress the eye cup to sort of simulate aging. Can we drip anything on that little eye cup that would slow it down? And is it safe? Using this, they already have a couple of hits for things, one of which is a nutraceutical. Not that I'm a huge fan of that industry, but there's something out there that in one of these assays seemed to slow degenerative processes in people with genetically determined retinal degeneration. Others are metabolic. It turns out certain sugars are better at keeping the retina healthy than others. And so you'd rather have fructose than glucose, for example. There are a lot of clues here that may allow us, in the future, to do bespoke assays. In other words, you come in with your particular eye disease, we grow the eye cups, and we ask, okay, is there something I could prescribe today that might be beneficial for you that we don't need to develop as a new drug? So we're really excited about this approach because it opens up an avenue to rapidly making progress to finding things that can help slow disease in a very scientifically rigorous way without having to go through a big drug discovery process. These are things that we can use immediately. All right, third vignette. And this one is work from my own lab, as well as my colleague Chris Fortenbach, who's an assistant professor in the department. And this is what we call chemical reanimation of the blind retina. And this is similar to the last vignette where we're trying to restore function, but here we're going to try to do it chemically instead of by stem cells. Now, as I mentioned, when we see retinal degeneration, and our model system is actually hereditary retinal degeneration or retinitis pigmentosa because we have better animal models for this. The rods and cones degenerate, but they leave the inner retina intact. So we have all the retinal ganglion cells which make up the optic nerve. We have these interneurons. Theoretically, if we could make these cells, which communicate with the brain, light sensitive in some way, we don't need rods and cones, because all the information that goes from the eye to the brain goes through these cells. If we can make these cells simulate what they would do under a normal circumstance, we bypass the needs for rods and cones and we can restore vision. So how are we working on doing this? Ginny mentioned going to meetings and learning. Sometimes these meetings seem like junkets to the outside, but they're really not. And this meeting in 2006 that I went to was definitely not a junket because it was in Palm Springs in July. This is the difference between PhD meetings and MD meetings. MDs go to Palm Springs in January, PhDs go to Palm Springs in July when the hotel rates are very cheap. So we're at this meeting and it is miserable. It was 114 degrees out. It was humid because it was monsoon season and we were stuck inside. And I happened to end up sitting next to a guy named Rich Kramer from UC Berkeley. And Rich had given a talk about a new chemical that they had started to develop, which they called a photoaffinity ligand photoswitch. So the idea of this photoswitch is you have, in the original one, 3 pieces. You have a drug at the end in blue. So in this case, this is a potassium channel blocker. You have an azobenzene moiety. If any of you are chemistry aficionados, it's a very interesting molecule. It's a double nitrogen bond that is photoisomerizable. It means when light hits it, it switches from its cis straight configuration or kink configuration to trans, which is in the straight configuration. And then there was a little sticky note on the end, which was an acrylamide. So what happens with this thing? Well, when a cell depolarizes, the channel blocker goes into the channel, and then that sticky end gets near some nucleophiles, which are little other sticky pieces on the protein, and it becomes bound. Now what we have is this ball basically stuck in the channel. And when you have a ball stuck in a potassium channel, that causes cells to depolarize and fire. So now we've made this neuron fire. Well, that's not that useful by itself. Basically, that would cause epilepsy if we just gave it to someone. But what's useful is if you hit this with one wavelength of light, you isomerize that double nitrogen bond, and now the ball has popped out of the channel. And if we hit it with another wavelength of light, now it pops into the channel. And what that does for us is if we take a retina of an animal out, and this is a blind mouse retina, a blind mouse with retinitis pigmentosa, and we're looking at a multi-electrode array. So there's 60 channels here going down, and each little tick mark is a firing of a cell on that array. So we're looking at least 60 cells here. This is the blind retina before we use the drug, and there's a 1-minute very bright light stimulant, which can either be ultraviolet or green here, and nothing happens. Now we put the drug on, wait 5 minutes, and we do the same thing. And now when we hit it, every cell fires. Okay, so using a chemical, we've basically converted the optic nerve into a photoreceptive cell, bypassing the needs for rods and cones. Does it work in animals? Yes, it does. So we took an animal that has no pupillary light responses, and we injected the eye with the chemical. And now what you're going to see is the lights turn on here. This is before and this is after the injection. Same light stimulus. And I think you can appreciate that this pupil is now starting to constrict, where in the same animal prior to the injection, there was no constriction. So there's no question that this is getting a signal to the brain that's capable of constricting the pupil. So that was meeting story number 1. Meeting story number 2 was a meeting that you might have said looked a little more like a junket, which was I was invited to give the keynote talk at the Royal Australian and New Zealand College of Ophthalmology, RANZCO, in Adelaide, Australia. And that was a real thrill to be able to go to Australia, meet my colleagues there. And I'm at the dinner for the speakers, and it was the weirdest dinner because they held it in a private box at the Adelaide Australian Rules football stadium with no game going on. So we're standing up in this luxury box. There's an empty field down below us, but I guess it was, a venue that they could get that evening. And this gentleman comes up to me and introduces himself, and he's the medical director for a very small company. And we start chatting, and I was going to speak about this the next day. And I said, what do you do? And he said, well, we work on a drug for adenovirus, which is a cause of conjunctivitis. And I said, oh, we're interested in that. We start chatting, and he said, what are you talking about tomorrow? And I said, well, we have some pretty interesting stuff of a preclinical chemical that we think might be useful in treating people with outer retinal blindness. He said, oh, my company's been talking about that. Tell me more about it. So at any rate, we chat. He comes to the meeting the next day, catches me after the talk. He says, I'm interested in this. Where's the intellectual property? I said, well, we don't have any of it. It's at UC Berkeley where the chemical was invented, but they have it licensed to a small company that hasn't done much with it. So I said, okay, thank you. A month later, he calls me back. He says, well, we've acquired the IP and we're taking this forward. I thought, wow, no pressure. So the compound they're taking forward is a second generation compound called BENEQ, B-E-N-E-Q, which my friend Rich Kramer synthesized originally. And this also has the effect of restoring light-dependent firing, but it has the advantage that you don't need a second color of light. So you can, in the dark, it relaxes on its own. And so it really simulates more normal firing in a retina. And there was a trick to getting it into the retina, which was to basically put it with an excipient, which was cyclodextrin, this big molecule here. And in animal studies, this worked pretty well to restore the pupillary light response, and it also seemed to be well tolerated. And so the company kicked off a clinical trial. And they're doing this in Australia, partially because it's much easier to do these things in Australia from a regulatory standpoint. By the way, I have no stake in any of this, so I don't have stock in the company. I don't have IP in this. I'm a consultant, unpaid consultant to them to try to get this out there. But the company really has done a great job pushing this forward. And they call the drug now Kiora, KIO 301. So they set up a clinical trial, a phase 1 trial, which is basically a safety trial to see if you could inject this into people's eyes and it would be okay. Short answer is it's okay. So no one got any, there were 6 subjects who got this. They were all very blind from retinitis pigmentosa. There were really no serious side effects at all in the study. So it seems to be well tolerated. But when you do a trial like this, you also want to see, did it work? So did it work? Yeah, it kind of did. So this is patients who had no light perception, whether they could see a stimulus on a screen of a very bright light. And there's a little tone to tell them that there may or may not be a light. It's calibrated, so it's less than 50-50. And what you can see is 20 days after the injection, basically their odds of seeing the light when it was presented doubled. So that was encouraging. There were some subjects in the test who had more vision than that. They could see a hand moving or even count a couple of fingers. Their visual acuity actually improved by about a half a log. And so that's going from hand motions to counting fingers. So that was encouraging. And their visual fields improved by about 20 degrees. So if they were only able to see that much in front of them, now they could see that much in front of them. That was encouraging. And then we had them do a maze test where they had to navigate through a maze under bright light conditions, but with obstacles. And again, 20 days in, they basically had they finished the maze in about a third the time. And the maze changes every time, so they can't learn the maze. All of this encouraging. And when we asked them whether this seemed to benefit them, their quality of life seemed to go up a bit as well. To me, the most impressive thing about this was looking at functional MRI. So for all of these subjects, we put them in an MRI scanner and measured their glucose uptake when we presented visual stimuli to them in the scanner. And if you look at this one, for example, at baseline, this is the occipital cortex. There's no response to a light stimulus. But on day 2, there's now a pretty robust response to a light stimulus. And we saw this in several of the subjects. Interestingly, in the sighted subjects, their effect was a little later. Not quite sure why that is, but all of the subjects showed an increase. And this is very objective data. You can't make your brain light up like that. It suggests that there's signal getting through to the brain after the drug. Now, many years ago, I saw a colleague of mine give a talk on a little chip implant for vision restoration that's no longer on the market. Didn't work terribly well. But I remember as a student being in the audience when he presented this, and he presented patient testimonials. And I thought, oh, that's the cheesiest thing ever to have patients talk. That's not scientific. So now I'm going to show you some patient testimonials because I think they're informative in terms of what the potential of this might be. So now this is in Australian. So for those of you who have difficulty with the Australian accent, it is closed captioned here. Whoops, can we turn the sound back up? Oh, okay. Yep. There we go. So, let me start that again.
At the start of the study, I had a couple of MRIs, and while I was there, and they flashed lights there, and I saw absolutely nothing. 48 hours after the drug, I had another MRI, and I think that was the first sort of OMG moment to say, what, I can actually see flashing lights. And that was an amazing experience to something that I haven't done for quite some time. One of the other times I think over the study that was a moment that you go, this is working, was I was laying in bed in a relatively dark room with my wife, and she pulled out her phone, and I just turned to her and said, can you see, are you using your mobile phone? Because I can see that the screen's on. And yeah, it was absolutely a definite, so I asked her, can you turn the screen off and turn it on? I'm going, I can see that when it turns on and off. And I can very much see the direction of the screen, the shape of the screen. And it was a really amazing moment from this study.
Now, this doesn't restore vision that he should go out hunting tomorrow, right? This is early steps, but the fact that we took someone who hasn't seen light or dark in 10 years, and now he has the ability to distinguish light and dark, we think that's a significant step forward. And now this subject had better vision at baseline. She was able to basically count fingers and see a hand moving. And her story is even more interesting to me. She's a little harder to understand.
We walked to the supermarket at night time, and I walked into the supermarket and I thought I was in a sci-fi movie. I'm looking around, and it was just bizarre because we're of course in the chocolate aisle. I could see everything, and I could see every individual item, which I wouldn't have been able to do at night time with all the spotlights and stuff. And I could see every item, every block of chocolate, all different colours. But the things that were bright were really bright, and the things that were darker were really dark. So everything was so itemised, and I thought Dr. Spock was going to be the checkout chick. It was just it was such a bizarre experience, but a good one. So that was a really good experience I had.
So I think here what we saw was an adjunctive effect of the drug on top of what vision that she had, which created something that was unusual, but at least to her seemed useful. So based on this, the company felt that this is worthwhile to pursue. And next month, the phase 2 study, which is a more in-depth study with more dose ranging and some other things, will start in Australia. That will go for about 6 months. And at that point, we'll see whether this has enough legs to get to a phase 3 trial, which is the official trial to try to get this approved. But we're very optimistic that we've made some progress here in restoring vision to people who have none, with a route that we can get to work within the next few years, not 20 years out or 30 years out. Now, to close out, Jack asked me to talk about the unique challenges of our time, and I don't want to put too much of a damper on this work that I've shown you, but all of you who watch the news or read the papers are aware we're in a very unusual time for science right now. I've been doing this, I think I first walked into my first research lab about 42 years ago. And we've never had a period like this where science has been under attack. And honestly, science is under attack. There's just a concerted effort to discredit scientific inquiry, to defund scientific inquiry, and really to block scientific advances. And we can debate about what the genesis of this is, but the net effect is that it's really impacting our ability to continue to do the type of work that I've shown you today. A lot of this has to do with the NIH. We have been, as I mentioned, very fortunate to be recipients of good support from NIH. This is your tax dollars and my tax dollars helping all of us because, as you saw, everyone has eye problems. This is something that distributes across the whole of our community. Eye disease does not care if you're rich, poor, black, white. It equal opportunity blinding diseases out there. What's happened for us, it's been a whirlwind this year, but the net effects are that there have been some administrative changes which have gone through the NIH, which have really cut the amount of funding that we expect we're going to get. One of these was a very evil genius move to basically say that the NIH should be funding grants up front. Currently, if I have an NIH grant, let's say it's a 4-year grant, it's $1 million. I'll get $250,000 in the first year, and then I have to give a progress report, show that we've made progress, and then they usually will give us the next $250 the next year. The memo that came from the NIH director said half of the grants, at least half of the grants in every institute now need to be fully funded in the first year. Now, at face value, that sounds great. I would love to have the $1 million in the first year. That we could do a lot more with that. The problem is the budget hasn't changed. And so by giving someone $1 million in the first year, that means 3 other grants aren't going to get anything. And what's going to happen is that the pay line for getting a grant accepted is going to drop dramatically, probably to a quarter of its current level. To give you an idea of how competitive that is, the research grants that we currently have, those 48 grants, all hit a pay line of at least the 13th percentile, meaning that of all grants, they were in the upper 13% at our institute. Most of them were in the upper 10%. Very few of them were in the upper 1%, though. That, in terms of judging against their peers, when you sent a grant in, there's a committee of your peers called study section that review the grants and rank them. And they give each one a score, and the percentile of that score determines what the NIH is going to fund. So at our institute, at the National Eye Institute, about 1 grant in 8 gets funded, which is better than a lot of other institutes. But 1 in 8 is still pretty competitive. What will happen with this is it will go to about 1 in 25. And this is the type of thing that we're up against right now to try to keep the research going. And the problem is if we have gaps in the research, we don't have $25 million a year sitting around to fill in the gaps. And basically things that will impact the research for years to come will happen, like research teams get furloughed or laid off. Animals have to be sacrificed because we don't have costs to continue to carry them. And the work just grinds to a halt. So it's been a uniquely challenging time for us. The administration has made it very clear that they would like to see NIH take a 40% cut. Thankfully, both Congress and the Senate in their appropriations bills that they can't agree on today, both left the NIH funding flat. The administration wanted to consolidate the NIH from 27 centers and institutes to 8, which would have led to folding of the National Eye Institute, so we would have had no funding agency for this work. Thankfully, that's not on the table this year, but it's just year 1 of this administration, so we'll have to see what happens going forward. If you would like to know more about what we do, we love to give lab tours, and Catherine Beard is here from our advancement office. If you'd like to come by and see the research, we would love to have you and host you. It's just up at South Lake Union, very easy to get to. If you know, a lot of people say, how can I help? We can use help right now. I've never in my 18 years as chair gone hat in hand to the community. I'm starting to go hat in hand to the community because we need some help to get some of these programs through this period to make sure the research just doesn't stop and people leave science, because that's happening. So, as I said, I don't want to leave on a down note. I want to leave on an up note. And the up note is really that I think research is getting to the point where we can make progress on these blinding diseases comparable to what we saw in the last century with cataract. We're enhancing our ability to eliminate blindness, even in this challenging financial climate. We're still able to protect our academic time. That is, our physicians are still able to do this type of research. We're still able to protect our teaching excellence and train the next generation and invest in our research infrastructure. So, as I said, this is my 3rd time having the privilege of speaking for you all. I hope that was illuminating and useful, and happy to take any questions. Oh, and we have a sign-up list that Catherine will have in the back for those of you who want to be on our newsletter. We also have our 2024 annual report if you'd like to read in more detail about some of the research that we're doing in the department. So thank you.
Thank you, Russ, for an outstanding lecture. And we now will take questions, we'll have mic runners on each section. And if you have a question, please raise your hand and somebody will come and give you a mic to look at. Here we go.
Thank you. That was really terrific. I have a comment question blended. When I'm reading about this attack on academia, science, I see it reported at an institutional level where it's the great big NIH, which a lot of people don't know about or understand, or Harvard, which everybody knows has deep pockets, probably beyond what the federal government has. But what I haven't seen and what I would love to see would be the kind of testimonials that you can provide as a researcher that are real in what is affecting people's lives, like the woman in Australia who got to see the chocolate. Anybody can relate to that, and that's not Democrat or Republican. That's just one comment about why, and my question is, why isn't the scientific community thinking strategically and talking to the people in that way that's not political, but talks about the real benefits of how public and private dollars invested in science can make a difference in people's lives? And thank you.
Yeah, that's a great comment. I think the scientific community is trying. And, if you look at our biggest organizations like the AAAS, the American Association for Advancement of Science, they are trying to get the word out as to why science is important. I mean, there are so many reasons, aside from the white hat reason of making people's lives better. If you look at the pharmaceutical industry in this country, which is a major industry, if you look at the Fortune 50, I think there are 4 U.S. pharmaceutical companies sitting up there. 98% of the drugs that are out there today started life as NIH grants, right? The numbers are that every dollar at NIH that's been spent over the last 20 years has yielded $7 of economic activity on the outside, right? So it's not like people are pouring money down a sewer from an economic perspective, let alone the quality of life improvements that we get when we have advances like this. So I know AAAS is out there. I know my academy, the American Academy of Ophthalmology, is out there. The problem is that there's so much, you can't just go on TV anymore and say, well, Walter Cronkite will interview us and we'll get the message out. Everyone's got their channels for getting news, and there are channels that don't care about this and frankly are not going to feature this. And there's a lot of people who are tuned to those channels, and they're never going to see this. So when I come to events like this, I feel often it's preaching to the choir. I mean, I think most of the folks here, and especially in Seattle, appreciate the importance of what we're trying to do. But you go to other parts of the country and you realize it's just a completely different axiomatic basis. And, at some point you can't argue axioms. You can only argue outcomes. And unfortunately, the outcome here is going to be, if things continue as they will, one, the U.S. will cede its research leadership in the world. That's already starting to happen. Number two, Americans will not have access to newest care. It's going to be innovated elsewhere, and you're going to have to go overseas to get your stem cell transplant or whatever. Third, we're going to lose a whole generation of scientists. And I say this as a parent with a PhD daughter and a master's comp sci son, both of whom aren't sure that they can make a career in the U.S. at this point and are looking at going overseas. In fact, our son is in Switzerland now. So, these are the long-term implications, and they're real. This is not, fake news. This is what's happening, boots on the ground. We had to close down our graduate program from admissions last year. We weren't sure we would have the funds based on what was being talked about in NIH to commit to students for 5 years or 6 years. And so we said, we're just not going to take students this year. What message does that send if you want to go into science? So all of these things are happening. I think there are a lot of people trying to get that message out, but it's being drowned in the cacophony of chaos that's everywhere. Very hard to get this message through.
Apropos of that, if you prior to what's been happening with this administration, if you looked into the future and you tried to plot a course in terms of the developments that you've described here, and the landmarks you would see in terms of some significant breakthrough in terms of, restoring impaired vision, how is that schedule changed now?
Yeah, so, I think that, for example, the stem cell work is going to grind to a halt because that's largely preclinical. There's not huge investment in industry in it at this point. There's a lot of things to work out, like exactly how do you do this transdifferentiation and what are the right proteins. And so I think that progress will stall if the funding environment, if the administration's desire for the funding environment, which was a 40% cut to the NIH, a cut in the indirect rates, which support, our buildings and infrastructure from 56% to 15%, and this administrative change on front loading the grants. In total at UW, that the three of those together will probably have an impact of somewhere around $700 million a year. Okay, a good fraction of $1 billion. This is in an institution, with a total research budget of about $1.5 billion a year. So it's about half of our research budget. You can imagine how that's going to grind a lot of things to a complete halt. Some of the other things that, like the small molecule photo switches, I think the first generation will make it to the finish line because it's in a commercial pipeline. But I can tell you that compound is not the best thing out there. We have 3 that are better in the lab right now. I'd love to see those follow on, and that work won't be able to move forward if we can't keep things going. So, obviously, if you're politically active right now, and again, I'm a state employee, I'm not advocating or lobbying for any particular position other than to keep the labs open. But make your voice heard if this is important to you. And in particular, I think our Washington representatives, for the most part, are very much on board with this. I think both of our senators have been extremely supportive, and particularly Senator Murray as the senior Democrat on the Appropriations Committee, fought very hard to ensure that the NIH cuts did not get into the Senate Appropriations Bill. But make your voice heard. People need to know that you're concerned about this because there's so many political issues right now, and people have to pick their favorites to advocate. You can't do everything. So absolutely make your voice heard.
I love your use of the term exciting. Is there anything exciting down the road for wet macular degeneration?
Yeah, definitely. So wet has been, a success story for us. So macular degeneration comes in 2 flavors, a dry flavor, which has no bleeding and no fluid, and then a wet flavor. And in the old days, what I used to tell patients was, good news, bad news on both. The dry form, the good news is it's very slowly progressive. It's not going to blind you overnight. The bad news is we don't have much treatment for it. And then the wet form, the good news is we have a treatment, but the bad news is it can blind you overnight. So the drugs that have come out in the last 15 years for wet, starting with Lucentis, Avastin, Eylea, Vabysmo, have been revolutionary. And if you look at the data, the burden of blindness in the United States has dropped by about 20% because of those drugs. They really prevent people with wet AMD, in many cases, from going blind. However, they don't last forever. And so people who start on treatment for the wet form usually keep pretty good vision for 5 to 7 years, and then it declines anyway as the membranes sort of become resistant and other degenerative processes take over. There's a very exciting clinical trial underway right now for a gene therapy that would put the anti-VEGF into a cassette where your own cells would make the drug continuously. You wouldn't need injections, and it would be there all the time. I think that's the most exciting thing that I've seen because that portends to be a one and done where you could be treated once and then essentially your cells would medicate themselves for the rest of your life if the virus stays active that long. So, yeah, exactly. And if you spend half your life in my waiting room or another ophthalmologist's waiting room getting your shots every month, it's a big deal. But we also think it will work better because right now we're sawtoothing the medicine, right? It's high dose and then down, whereas a virus can get sort of flat kinetics that should work better.
One thing you didn't address when you talked about the research in Australia. You gave us 3 months out. Is that durable, or is
No.
that needs another treatment?
Yeah, right now the medication probably has a half-life of 1 to 2 months in the eye. So we anticipate that, like with wet macular degeneration, if this gets to market, these folks will be coming in every 2 months to get re-injected. It's not ideal. But again, this is why we need next generation. And that's the work being done in my lab and Chris Fortenbach's lab that we're worried about going forward. So.
Any other question, please? One final question. If you look at the stem cell research, at one point you talked about the impact on the optic nerve. Mm-hmm. Obviously, I have a vested interest in that. Could you say a little bit more about that?
Yeah, so there's been significant progress. So the hardest problem in stem cell is really getting neurons to reconnect with each other correctly. We can grow the neurons. We can make optic nerve cells in a dish, but how do you make them connect? It's like a giant switchboard problem. The optic nerve in a young person has about 1.4 million cells in it. Each one needs to hit an exact place in your brain in the thalamus for the visual world to make sense. There has been pretty good progress in the last 3 or 4 years in figuring out the molecules that drive those decisions. Are we at the point yet where anyone has fully regenerated an optic nerve after a crush injury? Not yet. Are we much closer than we were 10 years ago? Absolutely. So I think there's hope in that domain, but I also, to be realistic, it's going to be a higher bar. So I think you'll see stem cells for dry macular degeneration first, because that pigment epithelial cells that I showed you with the nice hexagons, that's an easier problem to solve. Then you're going to see photoreceptors. That's the next easiest. And the nerve's going to be the hardest. So, but they all are part and parcel. The same research techniques apply to all of those.
Any other questions? Go ahead.
Does any of your work hold the potential to help childhood diabetics?
Oh, good question. In terms of their retinopathy. So the work I've shown you today, not really. Is there work ongoing on this? Absolutely. So that falls largely into that same wet AMD category. The same drugs that work for wet macular degeneration also treat proliferative diabetic retinopathy. And the problem with kids is when they develop it, it's a much harder problem, because you can't just have a kid in a 6-year-old in an exam chair lie back for an intravitreal injection. It's a trip to the operating room, and it's a lot to get treatment to them. So the idea, for example, of this gene therapy that releases anti-VEGF meds continuously has real potential in the pediatric space, particularly because it gets them more medicine earlier and doesn't require monthly trips to the operating room to treat them. It is a problem. I will say that overall, the degree of vision loss in this country from childhood diabetes has dropped about tenfold from where it was 50 years ago because of the implementation of laser therapies, panretinal photocoagulation, and these anti-VEGF drugs. So it's not solved, but it's usually a treatable condition. Very few kids go blind anymore from childhood diabetes unless it's caught too late.
Okay, if there are no further questions, this has been an extraordinary, thank you very much, President Gelder. Thank you very much.